Hello all, I'm Marco Gadola and I am a PhD student from Polytechnic di Milano. My thesis subject is low offset drift MEMS inertial sensors. Today, I will talk about the performance of a 50 kHz MEMS gyroscope based on piezoresistive sensing. Vibration rejection is a key parameter in many fields of application. For example, where harsh environments are involved in the military or automotive fields, but also in navigation, in inertial navigation and entertainment, where an external shock can cause an integration error and thus perturb the ongoing measurement. A viable approach in order to solve this issue is to move all the modes of the structure over the vibration bandwidth, much larger than 20 kHz. This comes with some disadvantage. First of all, in order to keep the same area, a frequency increase means a stiffer structure, thus limiting the displacement of both drive and sense motion. In order to keep the same sensitivity of a 20 kHz device, a higher power consumption is needed in order to move the drive frame by the same amount. Also, with the increase of frequency, there is an increase of quadrature error, and thus the need of more area or more power consumption in order to compensate it. In the literature, there are examples of vibration rejection devices. For example, a traditional capacitive gyroscope working at 100 kHz, bow gyroscope that are resonating at much larger frequencies in the megahertz range, and also frequency modulated gyroscope with a quad mass architecture. All three of them have some disadvantages. First of all, the traditional capacitive has the same problem we enlisted before, low sensitivity and high quadrature. The bow gyroscope has a high power consumption, and the frequency modulated one does not cope with both low noise and low power consumption. So our proposal is to use a different technology, the MEMS one, which allows to use a piezoresistive sensing with elements with a very small footprint. This allows to reach high sensitivity even at reduced displacement. Since it's a resistive technology, it is not affected by parasitic capacitances and their drift in time and temperature. Also, since the rotor must be kept at ground potential, a low voltage operation is allowed, even lower than 3.3 volts. So my presentation will describe the MEMS technology, the gyroscope produced with this technology, and then I will describe the characterization setup and the measurement performed with it. So the MEMS technology allows to embed in a standard 20 micrometer thick MEMS process thin piezoresistive beams of a highly doped monocrystalline silicon. This has a cross-section of 250 by 250 nanometers and exhibit a gauge factor of around 50. The output of the sensor is the resistance variation, which is directly proportional to the stress applied to the gauge. But since the drive and sense mass displacement are too high to be applied directly on the gauge, the amplification lever must be used. For example, in the animation, there is the sense lever, the amplification lever, in which the amplification factor is just the ratio between the distance of the gauge from the center of rotation divided by the length of the lever. This explains why it's possible to reach the same sensitivity for a 20 or a 50 kHz device, since it's just a matter of choosing the right amplification factor and thus applying to the gauge the right amount of stress. So also this explains why there is no trade-off in this technology between the frequency, the area, and the sensitivity. Since unlike capacitive technologies, there's no need to place more parallel plates sensing elements, but just moving the gauge in a different position. Also, low voltage operation allows to have minimum electrostatic effects like pulling voltage or electrostatic softening. So the gyroscope explained in this work was fabricated by CEA-Leti at their facility in Grenoble. It's a standard mode split dual mass tuning fork, which has here depicted in the picture in green the drive frame actuated by push-pull actuation, in orange the sense mass, and in purple the lattice work lever we've just seen in the animation a few slides ago. The drive frame resonates at 45 kilohertz, and the sense frame is frequency is mismatched from the drive by 1.5 kilohertz. I'd like also to point out that since there are no parallel plates, so much less area consumption, more area is allowed to be used as a sense mass, and thus more area is allowed to be used for quadrature compensation electrodes. In order to prove the vibration rejection of this device, a spectral analysis is performed by actuating the drive frame differentially and reading out from the sense ports. This shows that the only modes of interest apart from the first spurious one are the drive and sense modes. The first spurious is at 65 kilohertz, which explains the vibration rejection of the device up to 45 kilohertz. So the setup used for the measurement with this gyroscope is composed by an in-house built electronic board, a rate table linked to a lock-in amplifier. So the board has 4 main sections. First of all, the drive phase loop in order to keep under oscillation the drive mode. It has a Weston bridge in order to read out the gauge resistance variation, followed by a INA, a phase stage, and a gain stage. In order to keep the sensitivity stable, the drive displacement amplitude must be stabilized. And so there is a negative feedback loop, the AGC, which compares the drive displacement amplitude with a constant lever and changes the VGA gain. The sense chain is identical to the drive one with a Weston bridge and an instrumentation amplifier, followed by a lock-in demodulator. The demodulation signal is taken directly from the drive loop, and the lock-in amplifier has 2 outputs, the phase output and the quadrature output. The latter is used to close the automatic quadrature compensation loop that compares this signal with ground, integrates it, and uses the voltage acquired in order to polarize the quadrature compensation electrodes. I'd like to remember that this whole board is polarized at 6 volts, and the current in the gauge is 400 microamps. The sensitivity of the device is very simple and thus very stable in temperature. It's just a reference voltage divided by the mismatch frequency between drive and sense modes. The measured sensitivity is 1.37 millivolts over dps by the full scale range of the rate table, which is plus minus 3000 dps. The linearity error in the full scale range is less than 0.04%. Then an Allen variance is measured in order to measure both noise and the stability level. The noise is at 1.45 millidps over square root of hertz, and the bias stability is very low at 0.5 degree per hour. In the table here, there is a comparison between a 20 kilohertz device built in the same technology and this 50 kilohertz device. The 50 kilohertz device has a higher footprint, higher than 50% with respect to the 20 kilohertz, but shows much better bias stability of about 5-fold of increase and a 19-fold improvement in rate random walk. Making this the best performance 45 kilohertz in this footprint. Performances that are even better than most 20 kilohertz sensor nowadays on the market. In conclusion, in this work, an NEMS mode split gyroscope with modes at a high frequency was presented. It has a piezoresistive readout, and no modes are present in the vibration bandwidth up to the 45 kilohertz drive and sense resonating modes. With this device, low noise and high stability has been reached in an ultra small footprint sensor of about 1.45 squared millimeters. In the future, we are foreseeing the testing of a dual 50 kilohertz pitch structure with similar sensitivity in the same footprint, and also the design in the same technology of a 100 kilohertz yaw gyroscope structure. So my presentation has ended here. Thank you very much for your attention, and goodbye.